Okay, hello everyone. I welcomes to all in our lecture series on mathematical physics, that is your core paper 8 belongs to 4th semester BSc Physics on our syllabus CBCS model. Before we are going to start this lecture series, first we are going to discuss entire syllabus of this paper. This is the entire syllabus of this paper. First unit belongs to complex analysis, second unit integral transform 1, third unit is your integral transforms part 2, fourth unit Laplace transforms. In your first unit you can see that we are going to discuss brief revision of complex numbers and their graphical representations, Euler's formula, de Moivre's theorem, blah blah. These all the topics we are going to discuss in detail with note. Okay, this syllabus is your belongs to Utkal University, Odisha, and Delhi University. Exactly matched. If you are going to match with your Utkal University and Delhi University, this syllabus exactly it will match. And if you are belongs to other universities, then you can found more or less it is different. Okay, so let's start our first lecture upon brief revision of complex number and their graphical representation. So this lecture is your lecture number 1. Okay, so let's start. So this is your first lecture from your unit 1, that is your brief revision of complex numbers and their graphical representation, that we are going to discuss in detail with note. Okay, so here, to understand the complex number, consider two equations, that is your x square plus 2 equal to 0 and x square plus 3 equal to 0. If we are going to consider these two equations, then we can find that the roots of these equations could not be available in real number system. How it is? Here you can see, suppose we are going to consider x square plus 2 equal to 0. That means x square will be minus 2 and x will be plus or minus root over of minus 2, or we can write plus or minus root over of minus 1 into 2. But root over of minus 1 could not be found, or root over of minus 2 value could not be found in real number system. So we cannot find the roots of these equations in real number system. To find out the roots of this type of equations, we need another number system. Same thing that has been written. So to find out the roots of these equations, we need another number system which is called complex number system. To design the complex number system, the square root of minus 1 is represented as the symbol I, pronounced as iota. This symbol I was first introduced by Euler mathematician. Okay, that is I equal to root over of minus 1, or we can write I square equal to minus 1. Here I is your unit imaginary number. Now roots of the above two equations can be found or can be written by using I, as here I written. Just watch, x square plus 2 equal to 0, the above equation. X square will be minus 2, x will be plus or minus root 2, can be written as plus or minus root over of minus 1 into root over of 2. And as we discussed that minus 1 represented as iota or I, hence x will be plus or minus I root over of 2. So for this equation, it has two roots, that will be plus iota or I root over of 2 and minus I root over of 2. Similarly, you can do for this equation, and we can find the two roots are iota or I root over of 3 and minus I root over of 3. The above two roots are complex numbers. So these, if I am going to consider these two roots, or these two roots are the complex numbers which are exist in the complex number system or complex plane, that we are going to discuss later in our discussion. So these two roots exist in the complex number system or complex plane. In general, if we are going to represent a complex number which is represented as z, capital Z is represented as z equal to x plus I y. Here x and y are the real numbers, and x is the real part, is denoted by a real or rez of this complex number. This x is called as the real part of this complex number, and y is called as the imaginary part of this complex number, and in short it is written as 𝑍𝒂𝒑𝒊𝒂𝒑𝒊𝒐𝒏. Okay, see, this is the note that you have to write for your exam. In short, I have been prepared for your exam. Okay, now the use of the complex number we can found in various places in the science and technology. To study the conduction mechanism of material by complex impedance spectroscopy, we need the complex number. To solve many differential equations in electrical, electronics and communication engineering and fluid mechanics and quantum mechanics, etc., we need the complex number. Whatever you are going to found in your higher studies or in different core papers. Okay, now we are going to go for a simple question. Find the imaginary and real parts of the given complex number. Suppose we have a complex number that is your 3 plus I4 and minus 5i, and here minus 2 and minus 2i. What are the imaginary and real part of these given complex numbers that we are going to identify? For this bit, for a bit, real part will be 3 and imaginary part will be 4. The real part will be 3 and imaginary part will be 4. For this question, minus 5i, the real part will be 0 and imaginary part will be 5. How it is? Minus 5i, there is no real part. That means minus 5i can be written as, here minus 5i can be written 0 plus minus 5i, or 0 plus I into minus 5. So here real part is your 0 and imaginary part is your minus 5. Okay. Likewise, for C bit, the real part will be minus 2 and imaginary part will be minus 2 also. Now we are going to go for next question, that is your find out real and imaginary part of this question. That is your 1 plus I by 1 minus I. First we have to modify this given question in the form of x plus iy. In the form of x plus iy. How we are going to do? Here you can see x plus I by x minus I. Just multiply x plus I with numerator and denominator. We can found, here you can see 1 minus I into 1 plus I. So it will be 1 square minus I square. In the numerator we can found 1 plus I whole square. So 1 plus I whole square can be written as 1 plus 2i plus I square. And in the denominator, here you can see 1 square is your 1, I square is nothing but your minus I. Okay, so here I square will be minus 1 plus 1 got cancel, and this value is your 2. So we found 2i by 2 got cancel I. So I means this can be written as 0 plus I into 1. So for this question, real part will be 0 and imaginary part will be 1. Now we are going to go for another question, that is find the real and imaginary part of 1 plus I square by 1 minus I square. Same thing, to find out the real and imaginary part of this question, first we have to rewrite this given question in the form of x plus iy. To do that, here it is given that 1 plus I to the power 3, 1 minus I to the power 3. Okay, so first we have to rewrite in the form of x plus iy. Okay, so 1 plus I to the 3 by 1 minus I to the 3. We have to multiply 1 plus I to the 3 with numerator and denominator. In the denominator we can found in the form of a minus b and into a plus b. So it will be a square minus b. Here b is I to the 3 to the power 2, and in the numerator it will be 1 plus I to the 3 whole square. So the numerator will be 1 plus 2 I to the 3 plus I to the 6 whole divided by, here I to the 3 to the power 2 will be I to the 6, 1 minus I to the 6. Here I to the 3 will be nothing but minus I to the 6 will be minus 1. How it will be? Here you can see I to the 3 will be minus I. Here you can see I to the 3 can be written as I into I square. I square is nothing but minus 1. So minus I. I to the power 6 will be minus 1. How it will be? I to the power 6 will be written as I to the 3 into I to the 3. I to the 3 is nothing but minus I. So minus I into minus I. It will be plus I square is nothing but minus 1. Okay. So we found the numerator will be this much. 1 minus 2i plus minus 1 whole divided by 1 minus of minus I, because here I to the power 6 is nothing but minus 1, so it will be minus 1. So denominator will be plus 2, and the numerator here plus 1 minus 1 got cancelled, and numerator will be minus 2I by 2, and this will be I. So the real part and imaginary part of this given question will be how much? 0 and minus 1. How? This minus I can be written as 0 plus 1 plus I into minus 1 in the form of x plus I y. So here x is nothing but 0, y is nothing but minus 1. So real part of this given imaginary number is your 0, and imaginary part will be minus 1. So here one thing we faced, that I to the power 6 we have been calculated here. Here we have been calculated. So if somewhere it has been given some higher order of I, suppose I to the power 56, I to the power 256, suppose given in the question. So somewhat difficult to find out this higher power of the I. So here we are going to discuss to find out how to find out the I to the power any power, the value of I to the power any power instantaneously. So here we have faced a problem to find the higher power of I instantaneously. For that we have been calculated. See here, I to the power 6 I have been calculated by 2-3 steps, and here I to the power 256 also we need to calculate. But how to find out I to the power any order, I to the power any power easily or instantaneously? So find out, you have to write in your note that find out the nth power of I. We know that I equal to minus 1. I square is your minus I. I is your root over of minus 1, and I square is your minus 1, that we know. Now we have to find out I to the power n. Here n is any integer. The number n will be followed by either n equal to 2n or n equal to 2n plus 1. If n is your even, then it can be written as n 2n form. If n is your odd, then it can be written as 2n plus 1 format. Okay, so if n will be 2n, then I to the power n can be written as I to the power 2 small n. Okay, so here I to the power 2n will be equal to 1 if this small n is even, and I to the power 2n will be minus 1 if this small n is your odd value. That we are going to do 2-3 numericals. From that you will be clear about that. Likewise, if n will be written as 2n plus 1 format, so I to the power n will be I to the 2n plus 1. So here n will be, if n will be even, then this value I to the power n value, if it is written in the format of e to the power 2n plus 1, the value will be I. And if this small n will be small n will be odd, then this value will be minus I. Okay, so if the capital N will be written in the form of I to the power 2n, the value will be either 1 or minus 1. If it will be in the form of 2n plus 1, it will be either I or minus I. So here small n, if even, it will be 1. If odd, it will be minus 1. Here if small n will be even, then it will be I. If small n will be odd, then it will be minus I. Now we are going to go for 2-3 numericals upon that. So for this question number 4, find out I to the power 2656, that we are going to find out. Here 2656 can be written as I to the power 2 into 1328. So here 1328 is even, so it is written in the form of I to the power 2n form. So value will be 1, because 1328 is your even. Question number 5, that we have to find out 2654 value of I to the 2654. So 2654 can be written as 2 into 1327. Here 1327 is your odd, so I to the power 2654 will be minus 1. Question number 6, find out I to the power 653 will be how much? This 653 can be written as 2 into 326 plus 1. So here this is written in this format, so this value either I or minus I. Here you can see this n, small n value is nothing but 326, that means even, so this value directly we can write I. So if 651, I to the 651 will be there, then this can be written as 2 into 325 plus 1. Here 325 is your odd, so I to the 651 will be minus I. This is very important for different questions. Whenever you are going to find out higher power of I. Okay, you just remember carefully. Okay, these are another 3 questions for you. Do by yourself. Okay, I to the 765, I to the 7753, I to the 17768. So here suppose I to the power 6 what we calculated just before, I to the 6 if we are going to calculate, this will be I to the 2 into 3. So here 3 is odd, so we can write this value is -1 what we found. Okay, these 3 questions I left for you that you have to do by yourself. Next we are going to go for basic algebra of the complex number. Now we are going to consider 2 complex numbers. Let Z1 is your x1 plus I y1. Here x1 is the real part of this Z1 or complex number, and y1 is the imaginary part of this complex number. Z2, another complex number we have been considered over here, x2 plus I y2. The addition, if we are going to consider addition of these two complex numbers, so z1 z2 will be equal to, these are the very simple things. Okay, so x1 plus I y1 plus x2 plus I y2. So the real parts is going to be add with each other, x1 plus x2, I y1 plus y2. So the real part, this is the z dash, is the new complex number after the addition. So the real part of this z dash will be x1 plus x2, and the imaginary part of the z dash will be y1 plus y2. If we are going to consider subtraction between the two complex numbers, we found the real part of z dash will be x1 minus x2, imaginary part will be y1 minus y2. If we consider the multiplication of the two complex numbers z1 into z2, here you can see x1 plus iy1 into x2 plus iy2. You just multiply as normal multiplication. Here you can see x1 into this one, x2 plus iy2 plus iy1 into this much, x2 plus iy2. So here x1 is into x2, x1 into iy2, here iy1 into x2, iy1 into iy2. Here I means iota square. Okay, so that implies z dash will be equal to how much? Here you can see x1 into x2, and here iota square or I square is nothing but -1. So x1 x2 minus y1 y2 plus here I both common in these two terms, so taken common I, so x1 y2 plus y1 x2. So the real part of this new complex number will be x1 x2 minus y1 into y2, and imaginary part of this complex number, new complex number z dash, will be x1 y2 plus y1 x2. Very easy. Division of these two complex numbers z1 by z2. So x1 plus iy1 by x2 plus iy2. So for this case already we have been discussed here. Like that we are going to do that, we are going to multiply x2 minus iy2 both in numerator and denominator, and here we can found in the denominator this is in the form of a plus b into a minus b. So this will be x square minus b square. So a square means x square, x2 square minus iy2 square. So minus iy2 square means I square minus I square and into y2 square. So minus y square, I square is your -1, already minus is there, so it will be +1, so only y2 square. So in the denominator we can found x2 square plus y2 square. In the numerator you just multiply, here we multiplied x1, sorry, you just multiply. Okay, we can found after multiplication of these two numbers, complex numbers, we can found x1 x2 plus y1 y2 plus iota into x2 y1 minus x1 y2, and as denominator is a common term, so divided with this term x square x2 square plus y2 square, and divided with this term x2 square plus y2 square. You just check, rough. So from the above we found the real part and the imaginary part of the new complex number z dash will be how much? This one, x1 x2 plus y1 y2 whole divided by x2 square plus y2 square, and the imaginary part of this z dash will be this much, that is your x2 y1 minus x1 y2 divided by x2 square plus y2 square. Now we are going to go for some basic properties of algebraic operations of complex number. To analyze of properties of algebraic operations, consider three complex numbers such that z1 equal to x1 plus I y1, z2 equal to x2 plus I y2, and z3 equal to x3 plus I y3. These are the basic things we are discussing about the complex number system. Okay, addition is commutative. Z1, first one, addition is commutative. This is the first algebraic operation. Properties of algebraic operation. First one, z1 plus z2, we can find z2 plus z1. So x1 plus iy1 plus x2 plus iy2 will be equal to what we can found? We can found x1 plus x2 plus iy1 plus y2. If we are going to consider LHS part, this much. If we are going to consider RHS part, also we are going to get the same. Here we can get x2 plus x1. Both are same. x1 plus x2, x2 plus x1. Okay, so LHS will be equal to RHS. Likewise, you can do by yourself in your rough, and you can found z1 plus z2 plus z3. First you have just add z2 plus z3, then you have to add with z1 will be equal to z1 plus z2 plus z3. Multiplication is commutative. That is, your z1 into z2 will be equal to z2 into z1. Multiplication is associative. z1 whole into z2 z3 will be equal to z1 z2 whole into z3. These things you can prove by yourself. Very easy. Multiplication is distributive. That is, your z1 plus z2 whole into z3 plus equal to z1 z3 plus z1 z2 z3. Existence of multiplicative inverse. This point is somewhat important. That is, your z inverse will be equal to 1. That means if we have a complex number z, then it has also a inverse, that is your z inverse. If I will multiply with both z and its corresponding inverse, then we can find 1. Okay, so now we are going to find out z inverse. Let x plus iy. Z inverse will be how much? 1 by x plus iy. Okay, so to write this one in the form of x plus iy, just multiply x minus iy with numerator and denominator. We found in the denominator this will be x square minus iy square. Okay, and the numerator is as such, we have to write x minus iy. X minus iy, the denominator will be how much? X square, and this value will be how much? I square, means minus. It will be already minus is there. So here you can also I haven't written I square y square. I square is minus 1, so it will be plus y square. So z inverse, that is nothing but 1 by z will be equal to this much, x by x square plus y square minus iy by x square plus y square. So this is called as your multiplicative inverse of z. Okay, now we are going to go for some numericals. That is your question number 11. Write in the form of x plus iy. So here 1 by I is given. We have to write in the form of x plus iy. This type of question already we have been done previously. Here 1 by 1 minus I. So to write in the form of x plus iy, we have to just multiply x plus I by x plus I, numerator and denominator. So denominator will be 1 minus I square, 1 plus I. 1 plus I square is nothing but minus 1. So here minus 1 minus 2 will be, so 1 plus I by 2. So this can be written as 1 by 2 plus I into 1 by 2. So for this case, the real part is your 1 by 2, imaginary part also 1 by 2. 2 plus root over 5I by 1 plus I. We have to write this one in the form of x plus iy. Similar procedure, that we have to multiply 1 minus I and 1 plus I. Sorry, 1 minus I and 1 minus I, both in numerator and denominator. You just solve. We can find 2 plus root over 5 by 2 is your real part, plus I root over 5 minus 2 by 2 is your imaginary part of this given question. Next, it has been given that 1 minus 2i to the power 3 by 1 minus I into 2 plus I. So this is in the form of a minus b whole cube. Can be written as a cube means 1q is your 1, and minus b cube. B cube means 2y whole cube. 2y whole cube minus 3a square b. 3a square. A square means 1 square is your 1. B is your 2y. 2i plus 3ab square. 3a into a means 1, 1 into b square means 2i square whole divided by this one. You just multiply these two complex numbers, we can find 2 plus I minus 2i minus I square. Here you can see 1 minus this will be how much? So here I mistakenly written here, this will be 2 to the power 3 means 8. 8, this will be I to the power 3 is your minus I here minus, so plus I. So 8i minus this your 3 to 6 minus 6i, this will be here you can see I to the power 2, that is your I square will be minus 1, and here will be 2 to the power 2 is your 4. 4 into 3, this will be 12. Mistakenly I written okay 12. Okay by here you can see I square is your minus 1 and this will be minus already is there, so it will be plus 1 and this is 2, so this will be 3, and this will be minus 2i plus I will be minus I, and the numerator will be how much? Here you can see this will be minus 12 plus 1 minus 11, and this will be minus 2 plus 2i, 8i minus 6i plus 2i by 3 minus I. So here we not found in the form of x plus iy, this one. So further to find out x plus iy, what we have to do? We have to multiply this 3 minus I. 3 minus I is there, we have to multiply 3 plus I with numerator and denominator. So it will be minus 11 plus 2i into 3 plus I divided by 3 minus I into 3 plus I. Then you just go through the same procedure and you can find the answer. So here denominator will be how much? This will be 3 square minus I square, and numerator you just multiply and go through with the same procedure, and you can find in the form of x plus iy. I left for you, you do by yourself. Next we are going to go for graphical representation of complex numbers. First you just watch this figure what I drawn, and you draw in your note. So this is your x dash line, and this is your y dash line. Both are perpendicular with each other, and this axis is called as the real axis, and this axis is called as your imaginary axis, y dash. Okay, and this is the center O. Okay, we consider one point located at xy. P is the point located at xy. Its real component is your x, and is your imaginary component is your y. And z, complex number, is represented as one vector, that is your z equal to x plus iy. This is one vector represented from the origin O to that point. Make an angle theta. Okay, and its exactly mirror point, this one, is located at P dash, and its coordinates are x minus y. This is just exact mirror reflection of this point. And if I am going to consider this vector from 0 O to P dash is represented as z bar, or complex conjugate of this complex number, that is your x minus iy. Okay, so this is the representation of a complex number in the complex plane. So this plane is called as your complex plane. This is the representation of a complex number, and this is the representation of the complex conjugate of this complex number. So both are conjugate with each other. If we are going to consider this is the complex number, then this will be called as your complex conjugate of this number. If we are going to consider this is the complex number, then this will be called as the complex conjugate of this complex number. Okay, so same thing I have been written in the note. You can write in a note for your exam. From the figure, it can be found that a complex number z equal to x plus iy is represented as a vector OP in the complex plane. This x dash y dash is called as your complex plane. The location or coordinate of P, this point P, is xy in first quadrant. By considering x dash as a mirror, if I am going to consider this is the mirror, then the mirror reflected point of P, reflection point of this point P, is your P dash in the fourth quadrant, this one, located at x, y minus y. The Z bar is nothing but is your x minus iy is called the complex conjugate of z, that is your x plus iy. Here I am going to tell you one thing, that some books are represented complex conjugate of a complex number as z star. Okay, so z star also represented as a complex conjugate of a complex number. So here I represented complex conjugate as z bar. Okay, so no issue about that. You can represent a complex conjugate of a complex number by z dash or z bar. So in this note, I have been represented at each and every, wherever I represent the complex conjugate, I represented that as z bar. Okay, note, if P is the location of complex number, then P be the location of its complex conjugate, what I discussed. Okay, now we are going to go for the modulus of the complex number. So from here your main topics has been started, which will be asked in your exam as the questions. Okay, so carefully you have to watch, write down your note for your exam. The modulus or absolute value, modulus or absolute value of a complex number is the distance between origin O and the point where it has been located. So this length will be called as the modulus of the complex number. So it is represented as z mod, that is your distance from O to P. This distance O to P is represented by z mod, and the value of z mod obviously will be x square plus y square root over. If I am going to consider Pythagoras theorem, then it will be x square plus y square root over. Or we can write a real part. Say, see, x is nothing but the, if we are going to consider x z equal to x plus iy, so x is nothing but real part of the complex number and y is the imaginary part of the complex number. So we can write in this form as a real part of z square plus imaginary part of z square whole root over. From the figure it can be represented, it can be noticed that z mod equal to z bar mod. That means this length will be equal to this length also. Modulus of z will be equal to modulus of z bar. That means we can write, if we are going to consider z mod, that is your x minus y iy, so z mod z bar mod will be equal to x square plus minus y square root over will be equal to x square plus y square root over, which is nothing but z mod. Okay, now we are going to go for some numericals upon this. Here the question number 12, representation of complex number and its conjugate in complex plane, then determine the modulus. Okay, so here I suggest carefully watch this numerical. Okay, so first one, a bit, given that we have to represent the complex number, that is your z1 is your 2 plus 3i, z2 another question minus 3 minus 4i, z3 is your minus 2 plus 6i or i6. First of all we are going to consider this one. We have to find out its location and its complex conjugate location and modulus. So this is the complex plane. Here you can see, so with equal space I divided the real axis and imaginary axis, you can see. So this one is your 1 2 3 4 up to onwards, and from this side is your -1 -2 -3, and this is your imaginary axis. That means this length is your I told initially that I is nothing but your unit complex number. Here I, in the first page itself, is your, here I is called the unit imaginary number. That means this one. So this point is represents the I. Okay, or iota, right? Okay, now if we want to represent 2 plus 3i in this complex number, here 2 is the real part, 3 is the imaginary part. So 2 is the real part, 3 is the imaginary part, up to this much. So this point is nothing but is your P1 point, and this from 0 to P, the vector represents the Z1 complex number, Z1 2 plus 3i. Okay, and it's exactly mirror point here. You can found over here, that is your P1 dash and the location of P1 dash will be in the fourth quadrant, and the coordinates will be 2, -3. Here 2, and along this way we can found -3, or the location will be 2, -3. And this vector is represents the complex conjugate of Z1, that is your Z1 bar. Now we are going to go for the second bit, that is your Z2, that is your -3 -4i, -3 and -4i. So -3 means this one, -3, -4, -4i means here you can see this is your -i, -2i, -3i, -4i. So this point is represents the P2, that is your location is your -3 and -4, and from O to this point, this vector represents the Z2 as per the question. Z2, and it's exactly mirror point, this one here in the second quadrant, that it will be nothing but P2 dash location is your -3, 4. And this point, from O to this point, if I'm going to draw a vector, Z2 bar is nothing but called as the complex conjugate of this complex number Z2, right? Z3, now we are going to look at the Z3. Here Z3, -2 plus I6. -2 I6 means -2 is your real part and 6 is your imaginary part. 6 means I, 2i, 3i, 4i, 6. So this point is represents the P3 point. Look, and coordinate will be -2, 6, and this vector 0 to P3, sorry, O to P3 is your Z3, that is your complex number as per the question. And its exact mirror point will be here. We can found here in the fourth quadrant, sorry, in the third quadrant here. And the location will be -2, -6. And O to P dash 3 is nothing but Z3 bar, complex conjugate of Z3. In this way we can represent a complex number and its corresponding complex conjugate. Now we are going to go for the modulus of the given complex numbers. So here you can see Z1 is your 2 plus 3i, and just before we discuss that, the modulus is nothing but real part square plus imaginary part square root over, and the value will be exactly same with the modulus of its corresponding complex conjugate. So first one, that is your modulus of Z1 will be how much? Real part square. Here 2 square plus 3 square root over. Same thing it has written. 2 square plus 3 square root over. 4 plus 9 root over. It will be root 13. Similarly, if we are going to consider its complex conjugate Z1 bar, that will be 2 minus 3i. Its modulus also will be root 13. We can find both are same. Now we are going to consider Z2. Z2 means -3 minus 4i. Its complex conjugate will be how much? -3 square. The -3 is the real part of that complex number. -4 is the imaginary part of that complex number. So -3 square plus -4 square root over. We can found 5. And if we are going to consider its corresponding complex conjugate, that is your Z2 bar, then that is your -3 plus 4i. Then modulus of that complex number or Z2 bar will be also same, 5. Similarly, the Z3 modulus and Z3 bar modulus, Z3 given as -2 plus 6i, so its modulus will be -2 square plus -6 -6 square, means here I consider the complex conjugate. Okay, if I'm going to consider a complex conjugate of Z3, that is -2 minus 6i, so its modulus will be -2 square plus -6 square root over will be root over of 40. And likewise, if we are going to consider Z3 and corresponding modulus will be -2 square plus 6 square root over, also will be get the same value. Now we are going to go for the basic properties of complex conjugate. These properties are the most important, which will be required for different type of numericals, to solve the different type of numericals. So here Z bar to bar, complex conjugate to conjugate will be the same complex number. Here you can see, suppose we are going to consider Z equal to 2 plus 3i, 2 plus 3i. Okay, Z bar will be how much? 2 minus 3i. Then Z bar to bar will be how much? 2 plus 3i again. So that means Z bar to bar, complex conjugate to conjugate will be the same number. This is the first property. You can prove it by yourself. It is very simple. And Z bar modulus will be equal to Z modulus, that already we have been discussed. And another important, that is your modulus of the complex number. Here I written mistakenly that square of the modulus of a complex number will be equal to z into z bar. That means multiplication with a complex number and its corresponding complex conjugate. Here I am going to prove it. It is somewhat simple, that x plus y iy, suppose we are going to consider z, and z bar is nothing but x minus iy, and you just consider z mod will be how much? This will be x square plus y square root over, right? Z mod square will be how much? X square plus y square. Now you just multiply these two, z into z bar, that is your x plus iy into x minus iy. We can found x square, here x minus ixy, this will be plus iyx, this will be minus I square y square. So this is minus plus, both are same, xy or yx got cancelled, and this is x square, and this minus I square minus 1 minus plus y square. So both are same, both are same. Here you can see another property is your z plus z bar by 2 is your real part of z. This is one of the important property that you have to remember. Z minus z bar by 2i equal to imaginary part of the z. Simple thing that you can prove by yourself. Here you can see, suppose we are going to consider x plus iy plus its complex conjugate x minus iy by 2. Here iy minus iy got cancelled, 2x by 2 will be equal to x. This is nothing but your real part of the complex number. And if we are going to consider fourth property, that is your z minus z bar, it will be x plus iy minus x. If I am going to put minus, this will be minus, and plus iy by 2i. That means here x minus x plus x got cancelled, and this will be 2iy by 2i will be y, which is nothing but your imaginary part of the complex number. z1 plus z2 whole bar will be z1 bar plus z2 bar, whole complex conjugate of this one. First you just add both the complex number, then take the complex conjugate, will be equal to the addition of the corresponding complex conjugates. Likewise you can prove, this is the easy things that you can prove by yourself. Z minus Z2 whole bar will be equal to Z1 bar minus Z2 bar. Likewise, you can prove Z1 into Z2 whole bar equal to Z1 bar minus Z2 bar. And the final property is your Z1 by Z2 whole bar will be equal to Z1 bar by Z2 bar. These 3, 5, 6, 7 can be, you can prove by yourself. Okay. So these are the basic and important properties that you have to remember, which will be essential for your different type of numericals. So here we have to stop our first lecture. Now second lecture, lecture number 2, in our next lecture we are going to discuss Euler's formula, polar form of complex number, principle of argument, and some numericals. Okay, so thank you so much for watching this video. Thank you.